In this video I'm going to go through the setup of this topology that we see behind us, which is enabling layer 2 transport over a layer 3 data center interlink. So effectively here we've got two data centers with these two DCI links, and in DC1 we've got this DC1 access switch. In DC2 we've also got the same access switch. That is just a standard Nexus layer 2 switch. It's got an access port in VLAN 100 as ETH1/3, and then it's got a port channel with ETH1/1 and 1/2, which go up to these two DCI switches. So because that's a port channel, these two DCI switches are in VPC mode. The idea of this video isn't to go through VPC configuration, so that configuration is already in place on both sides. So we've got ETH1/4, which is our keep alive link, and ETH1/5, which is our VPC peer link. We've also got ETH1/2 here, which goes between on both switches. That's going to be a layer 3 transit link between the two switches in each data center. And then we've got ETH1/1 on all four switches, which is essentially the DCI connection. So the VPC stuff's already set up, the ACC switches are already configured, so all we're going to be doing is configuring the DCI switches. So just to make sure that everything is looking good with the VPC side of things, let's do a show VPC brief on all the switches to just make sure that everything looks good, which it does. Port channel 2 is our port channel which goes to the access switches, so we can see that's up, and currently there's only one VLAN on there, which is VLAN 1, but when we add later in the video, when we add VLAN 100, we'll see that appear there. So first things first, we need to sort the underlay out, so we're going to use OSPF. So I'll get everyone into configuration mode, and I'll use the handy secure CRT bit down here that allows me to send the commands to all the switches, just to enable us not to have to copy and paste a load of configuration. So first of all, we need to enable OSPF, so we'll enable the feature, and then we need to configure a loopback for the peerings. So we're going to have loopback 0, which is going to be used for OSPF and BGP. So what we're going to do with that is we will no shut it, and then on each switch we want to give it an IP address. So we'll start off with 10.0.0.1, and we will just iterate that last octet across all of the switches, just like that. And then we need to enable, or we need to configure OSPF. So router OSPF underlay, we'll log adjacency changes because why not? And then we need to come back into loopback 0 and say IP router OSPF underlay, and then put that in the backbone area. So that's it for the second for OSPF. Now we want to configure these interfaces, these physical interfaces should I say. So ETH1/1 is going to have a /30 on it, and then ETH1/2, because it's within each data center, we're going to use IP unnumbered and pin that to loopback 0. So just to make it a bit simple, what we will do is I'll do this configuration direct on one of the switches, just so we can see all the configuration rather than me typing it in down here and us not necessarily seeing what's actually going on. So ETH1/1, we'll say it's not a switch port. We will no shut it. We need to enable jumbo frames, so we'll set the MTU to 92.16. We'll enable medium P2P, and then we need to give this an IP address. So we'll say IP address 10.99.99.1/30, and then we also need to say IP router OSPF underlay and put that in the backbone area. So let's grab that configuration, and effectively we can copy and paste that. So the other side of this link, this is the interface that we're configuring at the minute on this switch. The other side of that is DC2 DCI1. So we can whack this on here and just change that to a 2. And then for a DCI2 perspective, we can change this, but change it from 99.99 to 100.100, and this side's .1, and then the DC2 side is .2. Perfect. Then from a ETH1/2 perspective, we will do something similar. So ETH1/2, we'll say no switch port, no shut, MTU 92.1.6, medium P2P, and then we'll say this is IP unnumbered with loopback 0 being used. We will also enable OSPF on there as well. So this configuration is exactly the same for all of the switches, so we'll just copy and paste this onto all the switches. And in doing that, hopefully we should, if I do a show IP OSPF neighbor, we should there we go, just needed to give it a bit of time, have 2 neighborships per switch. And if we do a show IP route for OSPF underlay, we'll see that we've got some routes in here now, and we should be able to ping between the data centers and between the 2 DCI switches. So 10.0.0.4 we should be able to ping from DC1. There we go. Try that again and get full set of pings, all 5. Perfect. So now that we've got connectivity, we can start looking at PIM for multicast. So effectively, what we're going to do is we're going to configure, because we haven't got any spines in this architecture. Normally in a standard spine and leaf architecture, you'd have the spines as BGP route reflectors, and you would also have them as the PIM rendezvous points. So we're still going to have, or we're still going to use Anycast RP in this topology, but all of the switches are going to be members of the Anycast RP group. So effectively, we've got fault tolerance across all of the VTEPs. So we shall configure that. So what we need to do is we need to enable feature PIM. We'll do that on all switches, and then I'll do the configuration on one switch first, just to show it in totality, and then I'll copy and paste that onto all the other switches. So first off, we need to set the RP address of 10.0.0.99, and we need to assign that to the group list of 224.0.0.0/8. Sorry, /4, not /8. And then we need to say IP PIM source specific multicast range, and that is 232.0.0.0/8. Now for the Anycast RP side of things, we need to say IP PIM Anycast RP, and then we need to give it the Anycast RP address, which is 10.0.0.99, and then we need to give it effectively all of the members of that Anycast RP group, which is essentially all of our VTEPs. So this is DC1, DCI1, this is DC1, DCI2, DC2, DCI1, and DC2, DCI2. So that's all good there. So we'll do a show run section PIM. We'll just get that initially on all the switches, and then we still need to create that loopback for 10.0.0.99, which we'll do now. So in loopback 1, we'll now shut that. IP address is 10.0.0.99 with a /32 mask. This does also want to come into OSPF, so we'll say IP router OSPF underlay, and we'll put it in the backbone area as normal. And now we're configuring multicast, we need to say IP PIM sparse mode. We do need to also do that on the other interfaces that we've just configured, but for the minute, let's just get this onto the other switches. Like so. And then on here we need to say int loop 0 IP PIM sparse mode, and then the physical interface is 1 and 2. We need to also say IP PIM sparse mode. So we'll do that across all the other switches as well. And in DC2 on the last switch. Perfect. So that's all the configuration required for PIM. If we do a couple of commands, we can do a show IP PIM RP. So this will show us the rendezvous point for the VRF default. So we can see in here that we've got all the members. So we've got 1, 2, 3, and 4. We can see there's an asterisk next to us because we're on DC1, DCI1. This is our IP, and then we can see the RP down here. The group it's 4, and there's an uptime ticking there. So if we do this on another switch, so one in DC2 for example, we'll see pretty much the same output, but we've got an asterisk next to the address for this switch. So that's a good sign that things are working. So now that we've got multicast, we can start to configure the NVE interface, which is effectively the VTEP interface, which is used for encapsulation and de-encapsulation of the traffic. So firstly, we need to configure another loopback. So Cisco best practice says that you shouldn't mix loopbacks for routing and for the VTEP. So effectively, we're going to create another loopback just for the VTEP. There is a slight caveat with that in my environment because I'm using VPC enabled switches. I need to configure a secondary IP address on those loopbacks, which are common between the VPC peers, which is essentially going to be used as a sort of a VIP. It's more commonly known as Anycast VTEP. Effectively, it's the IP that sits between both of the VPC peers, which is used on routing updates, so that any other VTEPs that are sending traffic to devices that are connected to the VPC pair send it to a VIP rather than a specific IP address of either one of the VPC peer nodes. So what we need to do is we need to configure that. So loopback 2, we'll say IP address is 10.0.1.1 for this switch, and then we'll also configure 101, and we'll say that is the secondary address. We'll now shut that. We will pull this into OSPF as well, and then we also need to say IP PIM sparse mode. So let's grab this because it's pretty much again the same configuration on the other switches. Instead, we just flip that to a 2. We will add a no shut to that just in case. So effectively, between these two VTEPs in DC1, this address doesn't change, but the primary address does. So just in doing that, I'll have copied and pasted something else. So what I'll do is recopy that, and then in DC2 we want to change that to 3 and this to 102, and then also add a no shut onto there as well. So let that do its thing, and then on the last switch we change this to a 4 and leave that as 102. So that's done from a loopback perspective. Now we just need to configure the NVE interface, but before we do that we need to enable some features. So feature that we need to enable, there's 3 of them. So there's fabric, forwarding, there's VN segment VLAN based, if I can spell it right. There we go. And then NV overlay. They're the 3 that we need for the minute. So let's come into interface NVE1. We'll no shut it. We'll say that the host reachability protocol is BGP. And then another VPC specific command that I'm going to put in here is advertise virtual RMAC. So what this effectively does is, instead of advertising the specific, I suppose it's not necessarily physical, but the specific device's MAC address for the NVE interface, we're going to use the VPC virtual MAC address that's between the 2 switches, which is effectively the same thing as doing this. It's essentially a VIP rather than one of the specific addresses of the switches. So we do get a warning here around BGP to say that we've got to also advertise the PIP into there, which we will do when we do that configuration in just a second. But the last thing we need to do in here is set the source interface to loopback 2. and then we can grab this and put it on all of the other switches. And again, we'll get that warning on all of the switches, as we'd expect. Just wait for that to go through. There we go. So that looks good on all of our switches. Speaking of that warning, we'll now look at configuring BGP. So we're going to use BGP as the overlay in the L2VPN EVPN address family. So we need to enable BGP, so feature BGP, and then in order to be able to use the L2VPN EVPN address family, we need to set a specific command, which is NVE Overlay EVPN. That effectively allows us to use that address family. So on DCI1, we'll come into router BGP 64.500. We'll log neighbor changes, because why not? We'll come into the address family of IPv4 unicast just to enable it, and then come out of there, and then come into address family of L2VPN EVPN, and this is where we say advertise pip. So because again we've got no spines, we've got no need for route reflectors really, because there's only 4 switches, so that means 3 pairings per switch. There's not really a great deal of pairings. If we were to have 1 route reflector per DC, we'd end up with probably the same amount of pairings, and having 1 route reflector across all 4 switches probably wouldn't be a good idea, because it wouldn't be good from a fault tolerance perspective. So what we're going to do is we're going to effectively configure a full mesh of pairings, which for that we'll use a pair template. So we'll say template pair VTEP in all caps. So these are going to be IBGP pairings. So we'll say remote AS is 64.500. We'll come and say update source is loopback 0, and then the address family of IPv4 unicast will say send community both, and we'll enable soft reconfiguration inbound. Then we also got to enable the L2VPN EVPN address family, and we'll say in here send community both. And then last thing is we need to configure the neighbors. So we're on DCI1, so we're going to have 3 neighbors. They're going to be 10.0.0.2. We're going to say inherit peer, and then VTEP in all caps. The other peer we're going to have on here is .3, same thing, and .4, same thing. So if we come all the way out of that, show run section BGP, that is effectively the full configuration that we want. So we can copy and paste this onto the other switches. What we just need to do is we need to change the neighbor commands. So this is DC1, DCI2, so it's going to be pairing with 1, 3, and 4. So we'll paste that in there. DC2, DCI1 is going to be pairing with 1, 2, and 4. And then last but not least, DC2, DCI2 is going to be pairing with 1, 2, and 3. So we'll let that take effect. And while that's doing that, we should hopefully start to see some neighborships coming up. So show BGP, L2VPN, EVPN summary. In fact, let me terminal width, just change it so it looks a bit cleaner. There we go. So we can see all of our neighborships have come up. If we do that just on all the switches, just to make sure, we can see we're all good there, we're all good there, all good there, and all good there. At the minute, we're not seeing any prefixes received because we haven't configured the L2VNI yet, but there's no traffic actively between those 2 devices, so we're not going to see anything trigger. So speaking of the L2VNI, we need to configure that. So we need to configure the VLAN. We need to map that VLAN under the NVE interface, and then we also need to, under the EVPN configuration, add that VNI and set the route distinguisher and the route target. So we'll do that on this switch first, and then we'll replicate that to the other switches. So VLAN 100, we'll set the VN segment to 100, 100, and then in NVE1 we'll say member VNI 100, 100, and then the only thing we're going to do under here is say multicast group, and we're going to configure that as 224.1.1.192. Ordinarily, you've probably seen in the other videos that I've done on VXLAN fabrics, I normally enable ARP suppression, but with this specific topology, because we don't have any layer 3 SVIs or any cast gateways, we aren't able to use, or Cisco say that we aren't able to use ARP suppression. It does work in practice. I've tested it, it does work. However, it's not recommended by Cisco to use it because really we don't have a layer 3 interface, so it's not really, it may have some problems, you know, and we don't really want that in a production environment at least. So after that, we need to configure EVPN. We'll say VNI 100, 100, we'll say it's layer 2, and then we'll set the RD to auto and the route target for both to auto. Cool, so that's all the configuration we need to do on one switch. So let's show run VLAN, show run interface NVE1, and show run, we'll do section EVPN, and then we'll just grab all of this, and I'll remove the stuff in the middle. So we don't want any of that. We don't need that, and we don't need that. So effectively, we are creating the VLAN, we're setting the VN segment, which is the VNID, which is used in the VXLAN packet. Then we've got the NVE interface, we're mapping that to the multicast group, and then the EVPN side of things, we're mapping it as layer 2, and we're setting the route distinguisher to auto and the route target in import and export to auto. So we'll put that on all the switches. And then after we've done that, what we should see is if we do a show VPC brief on this port channel now, we see VLAN 1 and VLAN 100 because it's configured as a trunk. If we do that on DC2 side, so show VPC brief, we can see the exact same thing, and we can see that it's going to be consistent on the other switch because it says consistency is successful. So in theory, the only thing to do now is just to actually test what we've done. So we've got two servers, one in DC1, one in DC2. This one is 10.1.1.1, and this one over here is 10.1.1.2. So we should, in theory, be able to ping between those now. So if we check, this is in fact 10.1.1.1, and if we come in here and we ping 10.1.1.2, it won't work immediately because ARP's going to be doing things in the background, but we can see ping 3, things started to work, and that is now working as we'd expect. We come across here and jump onto the other PC on the other side and just confirm this is 10.1.1.2. We should be able to do the same thing and ping 10.1.1.1, and it should work a lot quicker because now we've got ARP working in the background. So we do have connectivity, that's a good sign, but it's always worth doing some verification to make sure that everything looks good on the switches. So there's a couple of things we can do. We can have a look at the BGP routes. So if we do a show L2VPN, show BGP L2VPN EVPN. So one of the interesting things here is we won't see IP addresses in here because, like I said, we aren't doing anything layer 3 wise. There's no SVIs, no anycast gateways. The switch has no reason to need to know the IP addresses of the devices. So all we see in the Type 2 routes, the Type 2 EVPN routes, is we just see the MAC address. We don't see the IP address. If we had a layer 3 SVI and things like that, we would see the IP address, but there's no need for it because we're not going to be doing anything with that IP address. So it would be information that's not essentially required. So we can see that we've got MAC addresses here. They're pretty similar because they're virtual MAC addresses of virtual machines. But if we had a look at the MAC address of the PC in DC1, we can see that that is here ending 0900. So that's this one here. So if we scoped our BGP command for that MAC address, we can see that this is the local side of things. We can see that here. So if we did this same command in DC2, we should see some more information. So we see a few more routes. We can see that this is the route that has come from DC1, DCI1. This has come from DC1, DCI2. We can see that it's VLAN 100 because of the default calculation of the route distinguisher, where this is 32767 plus the VLAN ID. So if we minus 100 from that, which is the VLAN ID, we get 32767, which is the default number. And then this is our route distinguisher, and we can see that these have been imported from .1 and .2, and one of those has been marked as best, the other one not best, just because of the router ID, because it's got right to the end of the BGP path selection, and the lower router ID effectively wins. So this is our best route. We can see we've got that Anycast VTEP address in there as well, and also because we're using VPC, we've got a site of origin on there as well to as a loop prevention mechanism within DC1, and DC2 will have something similar where the address will be 102. So from a BGP perspective, that looks good. We can also do an L2 route command. So if we do a show L2 route and we say EVPN, and we'll get a couple of options. We'll get an option for MAC or MAC and IP. Normally in a standard VXLAN fabric we would use MAC IP because we've got Anycast gateways and stuff. If we did MAC IP for EVI 100, we'll see there's nothing in there. If we remove the IP bit, we'll start to get things in here. If we do detail, we can see that we've got our local server here, which is down port channel 2, and we can see that's been sent to BGP. And then we can see this is our remote entry here. We can see that it's come from BGP and it's been programmed into the layer 2 forwarding table, and this is where it's accessible. We can do a show MAC address table address and then look at this MAC address, and we'll see that it's in there, and it's kind of next hop, if you'd like, is the NVE1 interface, and it's this VTEP address, which is DC1. So probably last thing to look at would be multicast. So that ARP request that initially went over the DCI between the two servers will have been an ARP broadcast, which will have been encapsulated and put into, well, not encapsulated, but it will have been forwarded by multicast across the DCI using that 224.1.1.192 address. So if we do a show IP mroute here, we can see that we've got a couple of S, G entries here in the multicast routing table. One, because we're in DC1, one for the local Anycast VTEP address. We can see the incoming interface for that is loopback 2, which is the Anycast VTEP loopback. We can see that the outgoing interface for that is the DCI interface. And then we've got another S, G entry here, which is for the DC2 side of things, specified by 102. We can see the incoming interface for that is it's coming from the DCI, so it's coming in from ETH1/1, and the outgoing interface for that is NVE1, which is the VTEP side of things. So effectively, that's all the verification that we need to do. We can see that the ping is working as we'd expect. If we had more servers to connect, they would all have connectivity between the two data centers. But effectively, that is the configuration done. Just wanted to do a quick bonus bit here. I've got some packet captures going across the DCI links at the minute, both the top one and the bottom one. And if we do a ping between the two switch servers again, and then just cancel that, what I just wanted to show is that if I stop these a second, the ARP request or any kind of broadcast messages that are going across are in fact being carried by multicast. So we can see here, this is the ARP request from 10.1.1.1 saying where is 10.1.1.2, and we can see by the destination there of 224.1.1.1.192 that is being carried across the DCI using multicast.